Hi folks, today we're going to be talking about how to read and understand chemical formulas. So, we have two main objectives for today. First, we want to understand the difference between a pure substance and a mixture, and in particular what the heck a chemical actually is. And second, we want to learn how to read a chemical formula. Now, in order to read a chemical formula, we need to know about element symbols, superscripts, which are numbers that are written sort of just above and to the right of an element symbol, subscripts, which are numbers that are written just below a element symbol, and coefficients, which are the numbers that come in front of them. These three things are all parts of a chemical formula, so we need to understand all three in order to know how to write them. So first off, some vocab. We have individual atoms. Those are the things that you've been drawing in our work so far. Atoms are the most basic unit of a chemical element. Then we have elements. Elements are types of atom. They're defined by the number of protons that they have. So if you have an atom and that atom has one proton, by definition, that is a hydrogen atom. Any atom with one proton is hydrogen. If you've got an atom and it has 6 protons, it has to be carbon. Just because it has 6 protons, that is the thing that makes it carbon. So elements you can think of as types of atoms, and atoms you can think of as the smallest possible piece of an element that is still that element. Now let's move on to molecules and compounds. So molecules are groups of atoms that are bonded together. Here is what you would think of when you think of something like H2O, 2 hydrogens bonded to an oxygen. That is a single molecule. Now, molecules are the smallest possible piece of a chemical in the same way that atoms are the smallest possible piece of an element. I could have a glass of water, or I could have a water molecule. The water molecule is the smallest possible piece of water that's still water. If I make it any smaller, it's no longer water anymore. It's just hydrogen and oxygen atoms. So molecules are the smallest possible piece of a compound in the same way that atoms are the smallest possible piece of an element. Now let's take a moment and talk about pure substances versus mixtures. So elements and compounds, chemical compounds, are both what we call pure substances, which is to say all the little pieces that make them up are basically identical. 2 water molecules, regardless of whether they come from the Indian Ocean or the Atlantic or the vase that I've got flowers sitting in, are basically identical, right? It doesn't matter where that water comes from. An individual water molecule is still just going to be 2 hydrogens, 1 oxygen. That's it. On the other hand, we can have mixtures. Mixtures are when you have lots of different chemicals put together. I am a mixture. I'm made up of loads of different types of chemicals. There are probably thousands of chemicals that help make me up. Something like a pizza is a mixture. It's got pepperoni, which itself is made up of many different chemicals. It's got cheese, made up of many different chemicals, including things like lactose. It's got bread, which is going to be made out of carbohydrates and all sorts of other chemicals. So a mixture is basically something that's made of many different chemicals. Now, pretty much everything in the universe is going to be made up of either the building blocks of chemicals, elements, it is a chemical, or it's made of lots of chemicals. Those are the 3 options. With the exception of, say, a neutron star, everything is made of chemicals. If you can touch it, if you can feel it, if it's made of matter, it's made of chemicals. So the next time someone says, oh, I don't want to eat that, it's got too many chemicals, know that that statement is essentially meaningless. All of your food is made of chemicals. If you eat an apple, it's made of thousands of chemicals. The word chemical does not tell you whether something is healthy or not. It really only tells you, well, it tells you that it's stuff, because pretty much everything is chemicals. So, a pure substance, something like water, has a chemical formula. I can tell you that something is water because it's H2O. I can give you the formula for what water is. A mixture, something like orange juice, is made up of many different chemicals. So a glass of orange juice, there's going to be the glass itself, which is made of silicon. There will be citric acid in the oranges. There will be sugar, which is glucose. That's a chemical, C6H12O6. There will be water molecules aplenty. There will be cellulose in the pulp. There's a whole bunch of different chemicals that make up a glass of orange juice. But it's still made of chemicals, even if it doesn't have a single chemical formula. So anything that does have a chemical formula is a pure substance. So water has a chemical formula. That's H2O, 2 hydrogens, 1 oxygen. Table salt is NaCl, 1 sodium cation and 1 chlorine anion. Citric acid, the stuff that makes lemons sour, is C6H8O7, so 6 carbon atoms, 8 hydrogen atoms, and 7 oxygen atoms. So the most basic thing to start talking about when we talk about reading chemical formulas is the element symbols. So if you look at your periodic table, you can see that every single block on it has an element symbol. So the symbol for hydrogen is a capital H. The symbol for helium is a capital H and then a lowercase e. Element symbols will always be either 1 or 2 letters. The first letter will always be capital. If there's a second letter, it will always be lowercase. That means that you can tell when you've reached a new element because there will be a capital letter. I cannot stress how important proper capitalization is here. Normally, it's not something I care a ton about, but with element symbols, it really matters because you might be talking about completely different things if you don't capitalize correctly. For example, let's say you write a capital C followed by a lowercase o. That's cobalt. It's element number 27 on your periodic table. It is this beautiful bluish metal. However, if you write a capital C and then a capital O, that's carbon monoxide. It is a deadly, colorless, odorless gas, and if you have too much carbon monoxide in your house, you will die. You do not want to mix up cobalt, a beautiful blue metal, with carbon monoxide, a deadly gas. So that capitalization really makes a difference. We actually do care about it, and I need you to make sure that you pay attention to it. You also can tell that you've reached a new element because the C here is a capital letter. The O here is also a capital letter. So I can tell that that's 2 elements as opposed to cobalt where that lowercase o is part of the first symbol. Now, we also have charges. Charges will be written as superscripts. Now, the word superscript, super is referring to the fact that it's up high, and script is just referring to writing. So this is writing that goes up above. So if you've got something like sodium, sodium can form a cation with a charge of +1. And that plus goes up above the sodium because it's a superscript. You'll notice that even though sodium has a charge of +1, I only wrote plus. That's because chemists don't bother writing the number 1. Yes, really. In the same way that in math, you don't have to write a positive sign next to every number if you're just doing 2 + 2. In chemistry, if you've got 1 of something, we just assume it's 1. If I tell you in math, what's 2 + 2, you assume I mean what's +2 + +2. In chemistry, if I tell you something has a charge of Na+, you assume that means +1. Likewise, if I tell you that a chlorine anion has a charge of Cl-, you can assume that that is a charge of -1. Hydrogen forms a cation with a charge of +1. I just write H+. However, if you've got more than 1 charge, you do have to say how many there are. So oxygen can form anions, negatively charged ions, with a charge of -2. So if I want to write about oxygen, I would have to write O-2 or O2-. People do it either way, and I will accept either. So if you want to go O-2, or if you want to go O2-, you'll see both of those out there. It's really not a big deal which way you do it. Magnesium can form cations with a charge of +2. So I would write Mg. Notice the M is capital, the G is lowercase, +2. Or I could write Mg 2+. Either way is fine. So those superscripts, those numbers that go up above, those are our charges. Now, our subscripts, which are numbers that go a little bit below the element symbol, those tell us how many atoms of each element we've got. And again, remember, chemists are lazy about writing the number 1. A chemist never writes the number 1. So you'll notice there's nothing written here after carbon. That means that this molecule, CH4, methane, has 1 carbon. We assume it's 1 because we didn't write anything else, and 4 hydrogens. I can tell that there's 4 because there's a subscript that tells me 4 hydrogens. So those were our subscripts. Now let's talk about coefficients. Coefficients are numbers that go in front of the molecule. Now, while the subscript tells us how many atoms there are in a molecule, so for example, we've got 2 hydrogen atoms in H2O, a coefficient tells you how many molecules there are. So remember, hydrogen and oxygen, those are atoms. H2O, water, is a molecule. So we've got 2 molecules of water, each of which has 2 hydrogens and 1 oxygen. So in total here, I've got 4 hydrogen atoms, 2 per molecule, and 2 total oxygens. Sorry, that's written wrong. I should say 2 total oxygens. The coefficient applies to everything that follows it. So that coefficient tells us both the number of hydrogens and the number of oxygens because there's 2 molecules. So to review, when we are reading chemical formulas, we can use superscripts to show us the charge of an ion. We can use subscripts to show us the number of atoms in that molecule. And we can use coefficients to show us how many molecules total we have. So here we've got a model of sodium oxide. There are 2 molecules here, and each molecule contains 2 atoms of sodium and 1 atom of oxygen. That means that in total we have 4 sodium atoms and 2 oxygen atoms. All right. Good work, folks.